Thank you, Paul, for the introduction. And I would also like to thank the NSF, the National Science Foundation, for funding this trip. All right, without further ado, let's get started. Cool. So I'll go over the brief outline. So we consider a projective geometry that consists of the subspaces of a finite dimensional vector space over a finite field. And we use this projective geometry to define a Grassmann graph, which is known to be distance regular. Now, our goal is to recover the whole projective geometry from the combinatorics of the Grassmann graph. And with this goal in mind, we will obtain a number of results that describe the projective geometry in terms of the Grassmann graph. All right, so let's nail the preliminaries first. So we let gamma denote a finite undirected graph that is connected without loops or multiple edges with vertex set x, edge set e, and path length distance function partial. And two vertices, we say they are adjacent when they form an edge. And the diameter of D is the maximal distance between any two vertices. Now, for x in a vertex set, we define the set gamma of x to be all the vertices that are adjacent to x. And we say that gamma is regular with valency kappa whenever the size of gamma x is kappa for all vertices x. All right, now for the 10th time, I'm going to define a distance regular graph. I'm pretty sure it's like the 10th time for this week, but anyways. So we say that gamma is distance regular whenever for all non-negative integers h, I, and j and all x, y in the vertex set such that the distance between x and y are h. The cardinality of this set where the distance between x and z is I and the distance between y and z is j depends only on h, I, and j. And this cardinality is denoted by p, h, I, and j. And these two are some examples of distance regular graphs. All right, and from now on, whenever I say gamma, we just assume that it's distance. Okay, now we go over some intersection numbers. We define BD to be 0, C naught to be 0, and BI to be PI 1I plus 1, AI to be PI 1I, and CI to be PI 1I minus 1. So BI would be the number of things that are one further away from y, for instance, and the one that is adjacent to x. And C would be the one that is adjacent to x and one step closer to y. And a fact to note is for I between 0 and d, BI plus AI plus CI just turns out to be the valency of gamma. All right, now we talk about the eigenvalues. By the eigenvalues of gamma, we mean the eigenvalues of the adjacency matrix of gamma. And since gamma is distance regular, gamma has d plus 1 eigenvalues, and we denote them by theta naught, theta 1, all the way to theta d, and we can actually order them in a descending order. And one thing to note is that theta naught turns out to be the valency of gamma. Right, now we're going to define a projective geometry. So we let f of q denote a finite field with q elements, and we let n denote a positive integer. And we're going to let v denote an n-dimensional vector space over fq. The set P is going to consist of the spaces of V, and the partial order on P is just given by inclusion. And for L between 0 and n, let the set PL consist of the L-dimensional subspaces. Okay, from this, we can actually define the Grassmann graph. So the Grassmann graph has a vertex set PK. So if we have a projective geometry, we just grab all those k-dimensional subspaces, and then we can form a Grassmann graph out of it. And we're going to denote this graph by j, q, and k. The vertices x, y of this graph are adjacent whenever the intersection of x and y has dimension k minus 1. Okay, and this Grassmann graph is known to be distance regular. And from now on, whenever I say gamma, we just assume that it is a Grassmann graph j, q, and k. Right, so one proposition that's going to play a huge role, this is proven by BCN. It is that jq and k is actually isomorphic to jq of n minus k. So using this proposition, we can actually just assume without loss of generality that n is going to be greater than or equal to 2k. Now, in this talk, you might actually notice here and there that n equals 2k is going to show us something really interesting or something that is as absurd as dividing by 0. So we're just going to assume that n is greater than 2k for now. And under this assumption, the diameter of the Grassmann graph is just k. Okay, so in this talk, the idea of like q to the n minus 1 over q minus 1, this is going to appear a lot. So might as well use the notation brackets m to mean this quantity. So with this notation in mind, we can actually express the valency of j, q, and k as q times bracket k times bracket n minus k. And we can do similar things for intersection numbers and eigenvalues, and they are shown as follows. Okay, now we talk about a representation. So we're going to represent the elements of P, the projective geometry, as vectors in a Euclidean space. And we're going to do this in two stages. First, we consider the P1, which are one-dimensional subspaces of an n-dimensional vector space. And this is how we're going to do it. So we let E denote a Euclidean space of dimension brackets n minus 1. And remember that brackets was the q to the n minus 1, that thing. And a bilinear form of brackets. And for any v in the Euclidean space, we're just going to denote, the square norm to be the inner product of v with itself. Okay, now we're going to define this function that maps an element in P1 to E in the following way. So they have to satisfy these four conditions. So the first condition is that E has to be the span of v hat. So the hat is the function that we're defining here. So it's going to be the span of v hat where v is in P1. And for v in P1, the square norm has to be brackets n minus 1. And for distinct u and v in P1, we want their inner products to be -1. And the sum of all v hats should equal 0. So we can think of it as just putting the points on a sphere so that the distance between each two points are, a pair of points would be exactly the same. So that'll be a way to look at it. Okay, now we extend the function on this P1 to be the function that maps anything in P to E. And this is going to be rather straightforward because what we can do is we can define for W and P, the hat of W to be the sum of V hats where V runs through all the subspaces that are contained in W. Note that if W is in P naught, if it's just a zero-dimensional vector space, then we just let W hat to equal 0. Okay, now we're going to use this hat function to construct a representation on gamma. And to do that, let's go over some lemmas and corollaries. So the first lemma is that the dimension of x and y, x intersect y, is k minus the distance between x and y. Another lemma would be for u and v in the projective geometry. We have the inner product between u hat and v hat equals this quantity, where we assume that u lies in pi, v lies in pj, and u intersect v lies in ph. So from this, we can actually come up with a corollary because x and y are in a vertex set, which are k-dimensional subspaces. And using the the very top lemma, we can actually express the inner product between x hat and y hat to be brackets n times brackets k minus I, the k minus I coming from the first lemma, and then minus brackets k squared. And we have I to be the distance between x and okay. Some other corollaries that we can come up with is that the square norm of x hat, where x is a vertex, q to the k times brackets k times brackets n minus k. And two other lemmas that are important in saying that something is a representation is they're the following. So the first lemma would be the sum of the y hats, where y would run through all the vertices that are adjacent to x. If you sum them all up, you actually get a scalar multiple of x hat, and the scalar multiple turns out to be θ1, where θ1 was like one of those eigenvalues that we saw earlier. Okay, and the last lemma is that the vector space E is in fact spanned by x hat, where x belongs to the vertex set. Okay, so looking at these lemmas and corollaries, we can say that the Euclidean space E, together with the restriction of the map, W going to W hat to the vertex set, this gives a representation of gamma. Okay, next we talk about the symmetry of the projective geometry. Right, so the general linear group GLV consists of the invertible FQ linear maps from V to V. And the action of GLV on V induces a permutation action of GLV on the set P. And this permutation action respects the partial order on P. So if something was contained in the other, even after the action, that image of the thing that contained the other thing has to also contain its image. And the orbits of the action are PL. for L between 0 and n. So you can only permute within the same dimensions. Okay, from this we can define a stabilizer of a vertex, or it should be like basically any point on a projective geometry. So for U and P, we let stab of U to denote the subgroup of GLV that consists of the elements that fix U. And we're just gonna call this the stabilizer of U. And then from the stabilizer idea, we can further define the idea of fix U, and we're gonna let fix U denote the subspace of E that consists of vectors that are fixed by every element in this stab U. And one lemma that is not that trivial to prove, but it's pretty nice, is that fix U is spanned by U hat. So this is a pretty nice simple lemma. Now, things get a little more complicated when we introduce the stabilizer of two elements in P. Okay, so let's have a look at that. So for distinct U and V in P, we let stab of U and V denote the subgroup of GLV consisting of elements that fix both U and V. And again, we call stab UV the stabilizer of U and V. And similarly, we can define fix of U and V. We just let that be a subspace of E consisting of vectors that are fixed by every element of stab U and V. So the rest of the talk is going to be some, like intense description of what's going to happen within fix X, Y. So for the rest of this talk, we're going to fix distinct vertices X and Y in the vertex set. And we will display two bases for fix X, Y. So we first write I to be the distance between X and Y. And we're going to assume that I is going to be strictly between 1 and K for the sake of simplicity. The cases I equals 1 and I equals K, they're going to be of a different nature, and they're going to be handled in the paper, but not for this talk. Okay, so with these assumptions, we have a lemma saying that the dimension of fix xy is 4. Again, this is actually kind of specific for the case that I is between 1 and K and some other more cases. But for now, we just assume this I between 1 and K. And if that's the case, then the dimension is 4. Okay, and having that fact, we can actually come up with a theorem that says the vectors that form a basis for fix xy look like the following. So we have x hat, y hat, and then we have 2 more points on a projective geometry, the x intersect y and x plus y. We can actually have a hat of those, and those 4 vectors form a basis. And just for this talk, we're just going to denote, we're just going to call them the geometric basis because we derive these from the projective geometry. All right, so one thing we observe is that the construction of this geometric basis requires a knowledge of the projective geometry P. So what we're going to do next is we're going to try to obtain a basis that doesn't really involve a projective geometry, but only involves combinatorics of this Grassmann graph. Okay, so we define cal bx to be the set of vertices z, where z is adjacent to x and of distance I plus 1. And we're going to define cal c of xy to be the set of vertices that are adjacent to x and 1 closer to y. Note that these 2 sets, they are actually orbits of the stab xy action on gamma of x. Now we're going to define some vectors. So using these cal bx and cal cx, cal bxy and cal cxy, we can define the vector bxy to be the sum of all the vectors z hat, where z is an element of bxy, the cal bxy. And we define the vector cxy to be the sum of all the z hats, where z runs through every element of cal cxy. Okay, now we can come up with another basis for fix xy, and they would be x hat, y hat, and bxy and cxy. They actually form a basis for fix xy. And since we use the combinatorics to come up with this basis, we're just going to call these the combinatorial basis. Okay, now that we have 2 sets of bases of the same space, we can actually have transition matrices between these 2 bases. So that's going to be our next goal, and this is what it looks like. So one of them we can just have a we can express one of the elements in the basis as a linear combination of the other basis, and then we can just like form them into a matrix. And then the other one can just be obtained by taking its inverse. And one thing to note is that here at the bottom matrix, you realize that the brackets of n minus 2k is the denominator, and that's one of the disasters that can happen if you assume that n is equal to 2k. Now we introduce 3 more orbits of the stab xy action. So earlier we mentioned that cal bxy and cxy are orbits of the stab xy action on gamma x. And it turns out that there are actually 3 additional orbits, and we're going to describe these now. So since we touched on B and C, might as well just touch on A as well. So we define the set cal A of xy to be the ones that are adjacent. It's a set of vertices that are adjacent to x and of the same distance from y as x is to y. And the set gamma x is actually a disjoint union of cal bxy, cal cxy, or cal axy. It has to belong to exactly one of those. Moreover, the cal axy is the disjoint union of 3 orbits of stab xy. Now we can actually break this cal axy further into these 3 sets. So we're going to define cal axy plus to be the ones that actually lie in cal axy. But then if we look at their meets and the joins, we can actually see that axy plus is defined to be where the intersection of z, x, and y is exactly the same as just the intersection of x and y. And z plus x plus y is the proper superset of x plus y. Before I move on to the 0 part, I'm just going to define cal a xy minus first because it's just going to be symmetric in a way that it's going to belong to cal axy, but instead of the intersection, we're going to have z plus x plus y to be the same as x plus y, and z intersect x intersect y is going to be a proper subset of x intersect y. And cal axy naught is going to be the special one where it belongs to cal axy, and the pluses and the intersections, they're just the same as the original x plus y and x intersect y. So this is how we further break down cal axy. Okay, and these 3 are sure. Yeah. Okay, now these are orbits of stab xy, and cal axy is the disjoint union of these 3. So what we can conclude is that we can actually have gamma x be partitioned into 5 orbits, cal bxy, cal cxy, and then the plus null. Okay, now from these we can actually define vectors. So we define axy to be the sum of the z hats, where z is in axy, the cal axy, I mean. And then we can define axy plus, axy naught, and axy minus in a similar way as we have done before with like B, C, and the A. Okay, now by construction, we actually have axy plus, axy naught, and axy minus. They are in fixed xy. And we note that axy, the vector axy is just the sum of the 3 vectors that are listed below. Okay, next, we're going to express axy plus, axy naught, and axy minus in terms of the geometric basis, and this is what it looks like. So I guess before I move on, one might actually ask, so why do we actually care about these axy plus, naught, and minus? Why do we split them up into more cases or more sets? And I guess the short answer of that would be if I equals 1, then one of these actually play a huge role. And I'll just leave it at that, just to explain, like why is it important? So now we talk about the balanced set condition. So we consider several subspaces of fixed xy, and the reason why I do this is because in both geometric and combinatorial bases, they contained x hat and y hat. And the question is, can we actually come up with subspaces that actually don't have these 2 as a part of the basis? So that's the motivation. So in order to do this, we recall the balanced set condition. So this is the lemma that is proved by Paul. So we have bxy minus byx is a scalar multiple of x hat minus y hat. And cxy minus cyx is a scalar multiple of x hat minus y hat. And axy minus ayx is a scalar multiple of x hat minus y hat. And those scalar multiples are shown. And using this balanced set condition, we can actually define things like bxy bar, cxy bar, and axy bar. And these are how they're defined. So bxy bar is defined to be bxy minus lambda b times x hat. And we can define cxy bar and axy bar in a similar manner. And the reason why we define it like this is because if we define it this way, we actually get something pretty nice. And that is bxy bar turns out to be byx bar. Cxy bar turns out to be cyx bar. And the same thing happens for axy bar. So we can actually switch x and y, and we can have it preserved. Okay, now we can actually refine this balanced set condition. So we just had the balanced set condition on A, and we now have balanced set conditions on plus, not, and minus. So axy plus minus ayx plus is equal to lambda plus x hat minus y hat. And we can have similar lemmas for all the other nots and the minus. And the scalar multiples are listed below. Okay, and using this refined balanced set condition, we can actually define things like axy plus hat, axy not, not hat, axy plus bar, axy not bar, and axy minus bar. And these are defined in this fashion so that eventually we can have axy plus is equal to ayx plus, bars I mean, axy plus bar is equal to ayx plus bar. And similarly for the nots and the minus. Okay, so with this, we can actually come up with one subspace of fixed xy, and it goes like the following. So we let sigma be an element of GLV that swaps x and y. And we see that fixed xy is going to be invariant under sigma, because just because we swap x and y, it doesn't change fixed xy. On fixed xy, we actually have sigma squared is equal to 1, thinking about how if we swap x and y, and if we swap them again, then we just go back to the identity. So what we can see is that this action of sigma on fixed xy is diagonalizable, and it has eigenvalues plus and minus 1. Okay, so one of the eigenvalues being -1, we have this lemma saying that the eigenspace of sigma with eigenvalue -1 is spanned by x hat and y hat, x hat minus y hat. And looking at this lemma, we've seen x hat minus y hat a lot of times earlier. And from this, we can actually observe that things like bxy minus byx and so on and so forth for C's and the A's, the eigenspace above actually contains these. For this, let's see. So there are two eigenvalues, one, -1. Yeah, so it's from a four-dimensional space. All right, so that's that. So now we focus on the eigenvalue of 1. So we define fixed xy bar to be the eigenspace of sigma with the eigenvalue of 1. So those are the ones that are fixed by the swapping of x and y. All right, so now we see that fixed xy is going to be a direct sum of fixed xy bar and span of x hat minus y hat. So from this, you can actually see that fixed bar is going to be three-dimensional, and it's going to come up later, and this is what it looks like. So the proposition is the following. So we have these vectors that form a basis for fixed bar xy, and it's going to be x hat plus y hat, x intersect y hat, and x plus y hat. And for the similar reasons, we're going to call this the geometric basis of fixed bar xy. And similarly, we can have another basis for fixed xy bar, and it's going to be x hat plus y hat, bxy bar, and cxy bar. And for similar reasons, we're going to call these this combinatorial basis of fixed xy bar. All right, so just like what we did with fixed xy, we're going to have these two bases, and we're going to express the transition matrices like the following. So again, we express them as linear combinations of one another, and we compile them into a matrix. And we can see that the second matrix is going to be the inverse. Okay, so another lemma is that vectors axy plus bar and axy not bar, axy minus bar, they are contained in fixed xy bar. So that means we can actually express these vectors as linear combinations of the vectors in the geometric basis for fixed xy bar. And the proposition below says that it expresses in a linear combination of the geometric basis. Now, we can actually do better. We can actually find a subspace that is two-dimensional inside this fixed xy bar. And what we're going to consider is a subspace fixed x intersect y and x plus y. And this is going to be a subspace of fixed xy bar. And our next goal is going to be to find two bases for fixed x intersect y and x plus y. And we actually refined it much more in a way that we have a basis for fixed x intersect y and x plus y turning out to be x intersect y hat and x plus y hat. And you notice that we just completely eliminated the x hat and the y hat in the subspace. Okay, and again, we call this the geometric basis of this fix. In order to describe a second basis for fixed x intersect y and x plus y, we're going to define bxy check to be the same as bxy bar, but then cxy check is going to be cxy bar minus q to the I minus 1 times x hat plus y hat. The way we define this is to make sure that these checks, we actually want them to lie in fixed x intersect y and x plus y, and that's why we defined it this way. Okay, so knowing these checks, we can actually come up with the following proposition saying that we have a basis for fixed x intersect y and x plus y, and they are bxy check and cxy check. And we're gonna call this basis the combinatorial basis of fixed intersect y and x plus y. So now that we have two bases, we know what's coming up next. We have to come up with a transition matrix. All right, so these are the 2x2 transition matrices between the geometric basis and the combinatorial basis. So as you can see, this looks much neater and much nicer than the original transition matrices that we looked at for just fixed x, y. So this is gonna be an important tool that's gonna help me out. All right, so just for the sake of completion, we're gonna define axy plus, axy not, axy minus checks. And again, these are also gonna help me sometime in the future. And they are defined in the following way. So axy plus check is going to be the same as axy plus bar, and axy minus check is going to be axy minus bar. Axy not check is going to be defined slightly differently. It's going to be axy not bar plus q to the I minus 1 times x hat plus y hat. And this was an intention to actually have these checks lie in this fix. Okay, so it was kind of constructed that way, but observe that these checks are contained in fixed x intersect y and x plus y. Okay, now since we said that these are in fixed x intersect y and x plus y, we can actually express these as a linear combination of vectors in the geometric basis of this fix. And this is how they look. Okay, and just one last thing about stab, x intersect y, x plus y in this fix. Is that we have an orthogonal complement of fixed x intersect y and x plus y in fixed xy bar. And we're going to denote this orthogonal complement by fixed x intersect y, x plus y perp. And this perp is spanned by, so knowing all this, what are we going to do with these? So earlier we gave the transition matrix from the combinatorial basis for fixed xy to the geometric basis for fixed xy. So what are we going to do? What we're going to do is that we're going to write x intersect y hat and x plus y hat as linear combinations of combinatorial basis for fixed xy, and see if we can actually find vectors that play a role of x intersect y and x plus y in the Euclidean space E. And using this approach, we hope to recover P using only the combinatorial properties of the Grassmann graph, like such as the intersection numbers, like all this kind of stuff. Okay, so in summary, we first defined the projective geometry that consists of subspaces of a finite dimensional vector space over a finite field. And we use this projective geometry to define a Grassmann graph. And we know this is a distance regular graph. And we obtained a number of results that describe the projective geometry in terms of the Grassmann graph. And we also mentioned the goal to recover this projective geometry from the combinatorics of the Grassmann graph. So that's it for my talk. Thank you for your attention. That's a good question. So it's kind of like in the beginning stage, but I have like these crazy ideas that are going on. I guess one of them is like we already know that we already know the existence of things like twisted Grassmann graph, and like in the case of JQ of 2D and D, where D is the diameter, things can get pretty crazy. Yeah, like I've considered a few examples, like just like play with the numbers like here and there. And I have this idea that I haven't tried out yet, but I've talked to Paul about it, and he said it's looking promising. So that's a hopeful message. So yeah, we'll see how it goes. But yeah, that's currently where I'm at.
As you've got the post-set structure that like to sort of work inductively in some area, like you don't want to induct from JD 2 plus 1.
Right, right.
What happens if D is just 3 dimensional vector spaces, Google or something?
Right.
Is there some territory where this is enough to recover it? It was really nice. Cool.
I guess one thing I can recall from Jack Coulin's lecture was that it was something to do with how Grassmann graphs are uniquely defined. When what was it? It was like when something was like the max of 2D plus 2 and some other quantity. I can't remember exactly what that was. But yeah, so using that, we can actually see that some of the Grassmann graphs are definitely uniquely defined by their intersection numbers. So for those parameters, at least we can hope, or we should expect, that these x intersect y hats and x plus y hats are very nicely defined. And those that are not within that category, I wish to see something that is very exciting that is happening with the x intersect y or x plus y, such as they're not well defined on an E, to kind of show, okay, maybe this suggests that there may be another distance regular graph that has the same intersection numbers as the Grassmann graph, but actually is not Grassmann graph. So yeah, that's kind of that's kind of the idea. So like if we know that if we know that the parameters or the intersection numbers uniquely define the Grassmann graph, then at least for that case we can be like, okay, so this is what we expect. And actually continuing with Gary's question. So I tried d equals 1 case. Sorry, no. Sorry, k equals 1 case. So in P1, everything forms a clique, and that's pretty simple. Yeah, but I just checked just to make sure that things are looking okay. Right. Yeah. Things. Yeah.
Yeah. So just to recap, so we're taking this in stages. For the present stage, we're just trying to, in a comprehensive fashion, understand how the elements of the projective geometry relate to certain vectors that are defined combinatorially, the px, y, cx, y, whatnot. And so Ian is presently working on a paper about that. And once we've completed that stage, then we'll try to use it to recover starting with the distance regular graph with the same intersection numbers as the Grassmann graph. Try to use it to recover the projective geometry and thereby show that the graph is isomorphic to the Grassmann graph. That's looking into the future. So I think it's a very, very promising approach.
How much of this approach can be exported to the dual polar spaces? Suppose we have some form, we just restrict them to the totally isotropic subspaces. It looks like the same roadmap that we followed. Where does it get messy?
Well, I agree that this general approach, if we can understand it for the Grassmann graphs, should be able to modify it to attack any graph with classical parameters. We'll see. That's for the future.
Yep. Ada.
Well, it's very nice and interesting talk. My question is very simple. What happens when n equals 2D? Like I know we find that still.
Oh yeah. Right. So that's a good question. So I guess one thing that definitely happens is we're going to have a lot of linear dependence between the things that I just mentioned as bases. So for example, let's see, like I can't think of it exactly on top of my head, but it was something like xy, bxy, and cxy, they happen to be linearly dependent. And yeah, things get pretty messy. And hence we got a lot of like n minus 2k in the denominator because they're not so well defined, or you cannot really express this as a linear combination of things that are like linearly dependent, and then like something turns out to be 0 and things get pretty messy.
In that case, the dimension of that fixed space drops down to 3. Is that right?
Let's see, if n is equal to 2k, that would be the case when the distance between x and y is the same as the diameter. In that case, because x plus y is just going to be 0. No, sorry, x intersect y is going to be equal to 0. So hence we can just completely eliminate the x intersect y hat case. And I think if n equals 2k, that gets even more disastrous in a way that x intersect y and x plus y both turn out to be 0 when x and y are diameter apart. Yeah, and yeah, that's the mess.